Alright, name is Sonny Vidović, work for University of Texas. I'm just a half and half, so you gotta forgive me for speaking in English because it's a lot easier on me. But I do understand and speak Serbian very well, so I can do that if it's necessary. But give me a break and let me do my language. I got a company, run it, work for University of Texas majority of the time, and developed tremendous strategies in thermal technologies. So, why is it not going? All right, got a lot of experience, but I graduated also in University of Belgrade, so good to see my colleagues here. And I'll try to present what we found out in the latest developments, what really rocks the boat, and what we try to help everybody in the world to start using our way of thinking. So, man, this mouse is really not cooperating with me. Okay, the subject of this is basically the VAV air terminals. VAV stands for variable air volume air terminals, but we in Texas are kind of tired of this long expression, so we just call it box. So every time I call it box, think about the box. And box is nothing but a device that basically transforms the medium pressure to the low pressures. So, idea about the presentation is to help the design engineers in selection of VAV boxes, but specifically think about the details. If you're a design engineer and you are using this VAV, you basically are very limited to the people who sells the VAVs. So you are taught in a school to figure out what's the load of the space, then you just call somebody else and says, this is what I need, and that guy gets you what he's got. There's many manufacturers of those VAV air terminals or boxes that we try to kind of fit in our design, and the problem is that really nothing fits. You get only what they have in their bag. So there's a salesman, you said this is what I need, this is how many tons I need, and this is what I got, and rock and roll. Then you come to the user, and user is very unhappy, especially with the bills, with the energy consumptions, and the rest of the problems that we have. So you got to be extremely careful, and I'm trying to educate everybody how to behave in the particular steps so that their chosen product really fits the best of its requirements. So this is the VAV box. I kind of hard time seeing. Okay. So this is the VAV box, and in this particular thing, I'll just give you a little couple briefs what you need to pay attention for. So I hope everybody understands what VAV box is, and I hope you guys are using it here. It was developed a long time ago, 50 years ago, and basic thing was to reduce the consumption of the cold air from maximum to minimum. And I hope everybody's familiar. So let's go to the factors. The basic determination of what I'm going to use is diameter, inlet diameter. So when we do this, we just give a diameter of it, and we said I need a 6-inch, 8-inch, 10-inch, and we kind of go for it. What are the problems? The problems is that I need to determine what is the maximum and what is the minimum. Maximum, as everybody knows, it's a load calculation that I calculated based on my whatever you guys use, Energy Plus or whatever it is, and you come up with a number. So that number has to fit in an inlet. Now, the question is, hey, but what about my minimum flow? So that's the first thing. So I could actually do oversize, and I can do actually undersize the box. So this is the couple things that I have to worry about. If I undersize, I'm gonna of course have a bigger pressure drops, I'm gonna have a sound losses and da-da-da-da. So this, I don't think I have time to go into all this criteria, but let's go to the selections. So the first thing that I pay attention is basically the total pressure drop on the box, not the static pressure as most of the people would mislead you with. You gotta understand only total. And when we were establishing this, we based our inlets on the 2,000 feet per minute, which is your velocity through it. And then due to the delta P, or the pressure drop, you really don't want to exceed the 0.35. If you exceed the 0.35, you're really consuming a lot more energy than you should, which means your box could be a small or blah, 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 or not particularly designed to do the fluently. So 0.35 is very generous. If you can reduce this, that will be in your benefit to lower the fan energy. Number two, what most people forget about acoustics. In the United States, the biggest lawsuits come from not thermal, but basically acoustical complaints. They would just complain because it's loud, noisy, and this is, the whole noise will be right here, that you can do this. So your manufacturer would not tell you particular details of this VAV box, so you gotta be very careful what you're selecting. So always ask what is the discharge sound, what is the radiated sound, and then decide how that fit in the noise criteria of a particular room. Remember, that is a taboo, but that's not the topic of this. Guideline number 3 is the maximum, as I already said. That's very simple. If you just remember that you don't have to exceed, you don't ever exceed 2,000 feet per minute. When I was a student, it was 5,000, I believe, in Belgrade, so which was ridiculously high. So the pressure drop was extremely astronomical, and that's why the fans were big and big. So 2,000 you should limit. The less you go, the better it is. The 2,000, it's okay, don't exceed it, but when I have to design something, I stick with 1,500 because of the future developments. You never know if your load calculation will really meet the need. Somebody's going to be, as the previous presentation, it's more or less, so you get yourself a little reserve. So my recommendation would be 1,500, recommended 2,000 maximum. Number 4, comes to close to our topic, which is the minimum airflow. How do we do the minimum airflow, and why is the minimum airflow really important? Is, remember, when we have ASHRAE 62.1 now dictates that we're supposed to always have a proper ventilation for the people when they are in the room, and that gives us a feedback, and we're saying, hey, listen, but there is not going to be a people in unoccupied mode. So what do? Well, this is the key. This is the key of it. So minimum, it's basically controllability of that particular box. So if we know that our controllability is basically the key, how low we can drive that VAV terminal, that would be the answer to how to save the energy on it. So, okay, so controllability really depends on that probe, which is the airflow station that we use to determine the flow and adjust our flow depending on the needs of the space. So if we base our thing to it, we will figure out that there's only 2 particular sensors in industry that we use. One is based on the classic velocity pressure sensor that works with the pressure drop, and the other one that is the key of this is the thermal dispersion. So if this is the types that we put on a slide, and you can tell that the velocity, static velocity pressure sensors on the left, and you can see all these pipes, and basically there's nothing to it, it's just the pressure drop to the device. So everybody's familiar with that. The bigger pressure drop, the more accuracy you get. The problem is that the bigger pressure drops will get you the more acoustical and more fan energy. So what we figure out is if we use the classic thermal, if we use the classic velocity pressure sensor, the lowest we can go, it's 400 feet per minute. So how did we figure it out? It's basically the flow or airflow CFMs are calculated based on the formula 4,000 times square root for the delta P. The delta P is that pressure drop on the sensor. if we can say that the 0.01 is legitimate reading on that sensor, it cannot be lower than 0.01, it becomes particularly 0. That 0.01 in that equation becomes 400 feet per minute. So 400 feet per minute in a duct who is 6 inches will get you minimum 150, 160 CFM. Why would you want to bring 160 CFM in a space that is unoccupied? If it's unoccupied and you keep bringing 55 degrees air to it, you're going to have to reheat it. That reheat will cost you money. So that's what we're coming to it, and I said, let's basically change the sensor who can actually go lower than the 400 feet per minute. So basically, next door we found that actually people do make those sensors, and that is a thermal dispersion sensor that actually works basically on the principle that the flow would be theoretically calculated proportionally to exchange of the energy in the temperature side. So if to explain this on a simple way is that if we do know how much temperature changes in a particular space and we compare it to the baseline, we can always know how many air flow goes through the particular pipe. So measuring these sensors, we basically we did test a bunch of them, and they coming to about 100 feet per minute, very accurate. So if I use this particular sensor on my VAV terminal, instead of the pressure drops, which is limited to 400, and I'm now on 100, I saved a bunch of money, particularly on unoccupied modes. Now, just the beginning of the thing, development. So this is the sensor type comparison that we kind of compare what's better, what's not better. Most people will tell us, well, the little pressure sensor that we use for 50 years so far cost $10, and this sensor cost $500. So don't tell us that now we have to spend more money in the beginning. But calculating the normal space on about 10 universities, we came up to the payback is 1 to 2 years, depends on how good design was. So there's you can see a lot of good things coming out of this. Now, what we learned is, and we created this diagram that particularly explains the benefits of use of thermal dispersion sensor. This is the typical controls for one space, one air terminal, one thermostat. That you can tell there's the two different modes. There's an occupied mode and unoccupied mode. In occupied mode, it was extremely confusing for the people to understand what's occupied, what's unoccupied. So we basically changed this and we said let's call it in two different ways: the work going on and work's not going on. So it will be work on, work off. Work on will be based typically just on a time clock. So from 8 to 8 will be work on, from 8 p.m. to 8 a.m. will be work off. So if I'm on work mode, work on, you can split that thing now to unoccupied and unoccupied mode, which basically means people are in or people are not in. So if the people are in, I need to provide the ventilation and I need to provide the positive pressure for the building. If the people are not in, I definitely do not need to provide that portion of the people. And that is additional savings. So basically, when we said work on, we said, okay, this is how much CFM we're going to bring, and we say work off. That's where the tremendous energy saving comes. Remember, you have to bring the 55 degrees air no matter what. And if you're unoccupied mode, and if you bring a 400 feet per minute, which is 160 CFM, you got to reheat that 160 CFM to 90 on the most of the unoccupied modes. That is a third. That's where that payback comes back to the 1 year. You can study this and figure out how did we do that. We also work on and work off. We also spread it. So we really do not control just 72 degrees no more. We control 70 to 74 when it's work on and 68 to 80 when it's work off. And if all thermostats are satisfied and nothing is going on, we are allowed by 62.1 actually to turn actual units off, depending on every zone is satisfied. So on on installation. So, and we started this was a theoretical experiment that we started, and we picked up a couple of buildings and we just monitoring right now, and then we learned a bunch of lessons, what we did wrong. The first thing is we did not know how to install that sensor, what is the proper requirements for it, and the second thing is how is that sensor related to that damper. So if you look at this diagram right there, we determined that the proper installation, and this is not the perfect installation, it's just the proper installation that gives the good results. So it needs to have 2 duct diameters in the front and 1 straight duct diameter from the box parameters, not from the damper. If you see the distance between the damper and that sensor, it's kind of maybe 2 duct diameters. It still does influence the performance of the sensor, because you know how the air goes. The damper starts closing, there's a turbulence, there's all kind of things happening over there, but the results are decent to be acceptable. The proper way would be 5 straight diameters in the front and 3 on the back, which would cost more, so people kind of agree that, hey, this is the proper way of dealing with this. Also, we experimented how this sensor has to be. Is it the horizontal or vertical position, depending on the damper, so we established it has to be in the same plane. And you know, it's basically, we just created a tunnel and looked at the performance of the air, how that does. On this way, we guarantee that this sensor will go to 100 feet per minute very accurately, and about 5% on and off, which is pretty good. So remember, you're reducing it from 400 or 500 feet per minute as a standard sensor to 100. That's about 75% of the saving. And remember that unoccupied mode is more time than occupied in the most of the time. In the most of the places in universities, they go home about 8 o'clock. So you have another, 14 hours of just idling things. We cannot turn the buildings off due to the humidity and the ugly weather outside, so we gotta just run it. So running it without reheat is a huge thing. Another thing that we experienced is basically insulation. Sensor came just as a sensor because it was not used in air terminals. It was used basically in outside air ductwork. It didn't come up with any insulation. Insulation created huge problems because the thing starts sweating. Then we created this diagram, and we told everybody we had to extend the probe so the insulation can be actually tucked in, and we put Armstrong insulation as a hard part that we could compress the seal. So we learned the lesson on that. That bumped the price from that 1 year to 2 years, but it was a simpler installation. The third thing that we established was, it's not here on the diagram, it really ate our lunch on the fact that the sensor was really not constructed for the high pressure system, for the medium pressure system. The sensor was used for outside air and things in the low pressures. So when we installed it in the high pressure, we actually found out that this sensor leaks. So when it was leaking, and the sensor was giving us false results of having a flow versus not having a flow. So they created another spray that was now it's a spray-on proof, which would not be leaks ever going on, and improve the reading. What was happening is the dampers would be closed all the time, and due to the leak of the sensor, we would still think that there is a flow. So in one time I came into one hospital, and they kind of congratulated me how much energy we saved, but actually we figured out that the saving came from dampers being closed. Yeah. And the whole thing, so, how am I doing on time? I guess. Okay, almost there. So, I tried to squeeze all this research of 2 years in one thing. So, just pay attention, change your sensors for the classic delta pressure sensors to the thermal dispersion. It will pay back off very quickly. You're going to be a lot more advanced. You can follow the ASHRAE 62.1 requirements very closely. You can reduce the consumption of the energy. You can reduce everything. And the CO2 mode is going to be very simply regulated. Anything that you can do with the thermal dispersion is just go for it. We have 2 big manufacturers in United States. One is Aptron, and probably you guys heard about that because they most famous all over the world, and the other one that's coming very strongly from California is air monitor. The two different, they have the same product, but they have a two different strategy. Eptron brings the constant power to the sensor and compares it to the reference, and the air monitor does the opposite. He said they bring the not constant power, but they match the power that will be always the same temperature as the reference point, and on that they calculate. So it's a really simple process, very simple card that you can get it in China. Probably those boards very simply, and they assemble it. Cost about, Eptron is about $600 a piece, and air monitor goes about $350 to $400. So guess what we're going with. All right, so that was to just give you the basic requirements for the selection of the VAV terminals based on the inlets and based on the norms that we in the United States use when we design. So that would be, I hope that's helpful. And I hope that I did not go over the expectation.
Thank you.